Hello, I'm Neeraj. So today I will explain the concept of W GAN or Wasserstein GAN. In the previous tutorial, I have already explained the concept of Wasserstein distance and how to use the Wasserstein distance for W GAN architecture. So now we will go through the architectural overview of W GAN, and after that I will explain how to write the code for W GAN architecture. So let us start with input data. So generally we take the two type of input data. First is the real input and second is the noisy input or random input. So to get the noisy input we use the normal distributions with mean 0 and variance 1 so that we can have some control on the noisy input data. We pass it through the generator model. The architecture of generator model is very much similar to the architecture of generator models in other GAN architecture. And after that, when it generates the images, we feed that image to the critic model or discriminator model. The discriminator model try to identify that how far it is from the real image. In the earlier cases of traditional GAN architecture, we say that the discriminator model generally classifies that whether it belongs to a particular real image class or fake image class. But here it computes the distance by using the Wasserstein distance, that how far it is from the real image, and based on that it generates the cost. So here you can see that the real image and then fake image, then they calculate the Wasserstein distance and then use that distance measure, pass it through the critic model, and then critic model uses this cost function and apply back propagation and updates itself. At the same time, the cost functions give like how the generated images is different from the real images. That information the generator uses and updates itself. So this way the entire system goes. For the real images, we are actually using the MNIST dataset. So I have already explained in the previous tutorial that what is the MNIST dataset. It is actually the number written from 0 to 9 and human entered numbers, and its size is 28 into 28 pixels, and it contains 60,000 training images and 10,000 testing images. And next is how the generator is working. So generator takes the noisy input data, then pass it through the dense layer, then reshape it to some 7 into 7 into 128 size, and then apply the deconvolution operations by using conv 2D transpose, and then applies the batch normalizations to avoid overfitting or any other and to balance the data. And after that it passed through another conv 2D transpose layer and then batch normalization, and then it tries to generate some real looking like number. So the role of conv 2D transpose and all other things are actually explained in the previous GAN related code, so I am not explaining that. So the next part is the discriminator. So in the discriminator you can see that it takes the real and it takes the input real and generated input and pass through the convolution layers, and it just like a convolution layers, and it decreases its size and then apply the Wasserstein loss functions so that it can identify the distance between the real and fake images. Now to train this system we will go through the what kind of algorithm it uses. So here you can see that. Now let us go through the basic algorithm as discussed in the paper. So main part of this WGAN architecture is the how to train the system with the help of Wasserstein distance. So in the training phase, as I already discussed, it uses Kantorovich-Rubinstein's duality and one Lifshitz function. So how it works, I already discussed. Now it is like how it controls the entire training and how it clips the gradient is actually discussed here. I think it will be more clear if we go through the coding example directly. So let us go through the coding example directly. Then I think it will be more clear. So here I have written the code. Okay, so first of all, you can see that we prepare the data set. We just take the MNIST data set, we load it. But instead of taking the entire data set, we just load the first 1000 samples, and then we just an additional dimensions, and after that we just convert it into unsigned ends to the floats from 0 to 255 to 0 to 1, and then return that data. Now the generator function, you can see that we take the input shape is actually equal to latent dimensions. That latent dimension is like the dimensions of the normal distributions, that data that we are using, and image shape is like 28 into 28 into 1. So height, width, and length, height. So image shape is like 28 into 28 into 1. So we first reshape that data, and after that we upsample it by using conv 2D transpose. So here we are using the filters 128, kernel size 4, strides 2, padding same, activations Likirelu, and then we again apply the batch normalizations to avoid any overfitting, and again we apply the upsampling stages. So how to use the upsampling and what is the role of upsampling in the generator case, that is already discussed in my previous tutorial, so you can go and check there. And after that we define the model, input and output. So our output, in the output case we have used the activation is equal to 10h, and padding same, and image shape equal to 2, and image shape that is actually 28, and then you can see that it generates the model summary and returns the model. So this is a generator model. The main aim of generator model is to generate the images. The next phase is like how to write the critique. So the critique part, you can see that we have take the input like a input shape, image shape, and after that we apply the convolution layers. So convolution layers are like conv 2D filtration, kernel size 2, stride 2, activation Likirelu, padding same. So all those things are actually discussed in the previous GAN tutorial also, because I try to maintain the same code with minimal changes just to achieve the WGAN architecture. So for the WGAN architecture, we have made the changes like instead of using the Adam optimizer, here we use the RMS prop optimizers, and for the critique model we use the Wasserstein loss function instead of binary cross entropy loss with respect to the GAN architecture. I had already discussed the previous GAN architecture earlier. So here you can see that in the previous tutorials, like earlier we had used loss, binary cross entropy, activation, sigmoid, but here in the case of WGAN we didn't use that. We use the dense equal to 1, no activation function, and loss equal to Wasserstein loss, and then we generated the model summary. And after that we designed the WGAN architecture. So input shape, latent dimensions, then generator output. Generator output actually we have defined the generator output functions, and then we use the output of this generator function as a input for the critique. So we first define the critic input, and then we define the critic output model, and then we pass we define the critic model also, and after that we compile the critic model, and then we say take the critic trainable equal to false, and then we generate the GAN output critic. We pass the generator output model to the critic so that we can get the actual critic output or GAN output, and then based on the GAN output and the latent input, we design the final WGAN architecture which take the latent input and GAN output, and then finally we compile the WGAN architecture by using the Wasserstein loss optimizer equal to Adam we kept here. But earlier you can see that when we defined the GAN architecture, we did something different, we used the binary cross entropy. And after that we train and save the model. So here we have used the gradient clipping. So first of all we use the training data set. We have taken the training data set, then we have identified the generator model, critic model, WGAN model, main model, and then we have identified real Y, fake Y, and then for number of epochs and for the number of batches in the data, and again we generated the noise also, and for number of critics so that we can properly apply the gradient cleaning. For that we use the number of critic, and we set the critic model trainable equal to false, and after that next we extracted the real data set from the real data from the actual data set, NX data set, and then we took the Y real that from real Y, and after that we just use that real data set to train the critic model, and after that we take the fake sample and then fake Y value, and then we train the critic with the fake data set, and after that for number of critic loop we just apply the gradient clipping, and after that we make the critic model trainable equal to false, and after that we finally train the final GAN model, and then we save both models. To call the main function is very easy. Here you can see that input shape, image shape, latent dimensions, number of critic equal to 5, clip value we have put 0.01, and then we call the class function, and then G model, GAN model, and then we train and save the models. We call this to train and save the models. So once we train and save, you can see that it works like this. So this way you can see that it is training number of epochs. So we are just using 2 epochs training, and then you can see that how the cost function is going on. So batch mode G loss functions. I am going to close this because it may take a lot of time. Now actually I trained a model on the same 2 epoch, so we can easily test it. Testing process is very much simple. Just load the generator model, and then apply some noisy data, and then try to construct some images from that noisy data. So WGAN test. So here you can see that actually for just 2 cases I think it is very tough to generate any real looking images. So if you train the system for multiple epochs, like 100,000 epochs, then you will get a very good result. And to properly understand all the part of this code into more depth, you can watch my previous tutorial on GAN architecture. So thanks for watching.